All right, so again, notes in the margin. We should definitely know that already. Okay and no. 0 in the top is 0. 0 in the bottom is undefined, but more specifically, it's infinity or negative infinity, because you're dividing by a really, really small number. All right, evaluating one-sided limits algebraically and limits at infinity algebraically. So yesterday we evaluated limits. What's new today is one-sided limits and infinity limits. Well, the good news is that the first technique is the same. Substitution. Plug it in, see if it works. If you get something nice, then you're good. Let's see how to phrase this. If you get, let's go in order. If you get 0 over 0, then see worksheet 2, right? Like then we got to use one of the tricks from yesterday. That was yesterday's issue. Let's see, that's statement 1. Statement 2, if you get okay, if you get 0 over something, then the limit equals 0. So that's probably our most preferred method, because that doesn't require any other work. If you get something over 0, then is it positive infinity or negative infinity? So that's kind of the path for today. There's going to be zeros in places, and we got to know how to handle them. If it's 0 over 0, then we got to back up and do one of the tricks from yesterday. That's not going to happen much today, because that was yesterday's issue. But thinking big picture, if that happens, then you got to do one of the tricks, algebra tricks. If you get 0 in the top and a number in the bottom, that's great. That's just 0. We're fine with that. If you get a 0 in the bottom, that's going to be our big concern for today. That'll sort of be the focus of today, because we already did case number 1. Case number 2 is pretty trivial because it's just 0, and then case number 3 is we're going to have to think about things a little bit. All right, so let's do some examples. Let's look at number 1. X approaches 3 from the right. Okay, so from the right means a little bit more than 3. But our first go is we can just plug in 3 and see if it works. And if it works, we're fine. We don't really have to worry about the plus or minus business. So 3 squared plus 9 over 3 cubed minus 10. Let's see. 9 plus 9 is 18. 27 minus 10 is 17. There's nothing wrong with 18/17. We're good. And so the plus and minus thing on that didn't matter. So we like those. So as always, that would match to just substitute and don't worry about the plus or minus. Then if you get something weird, then we got to worry about things. Let's jump down to number 4. Speaking of worrying about things. So if I plug in 2 minus 5 over 2 minus 2. Well, that would be negative 3 over 0. Uh-oh. So this is our uh-oh case. So it's going to infinity, but I need to be thinking if it's positive infinity or negative infinity. So I need to know if that 0 down there is like a positive 0 or a negative 0. Well, so it does matter on this one, 2 plus. So this is where things get a little bit weird and people start to look at me like I'm crazy, because I'm going to substitute 2 plus. A little bit more than 2. Let's see what happens. So a little bit more than 2 minus 5. That's still negative 3. And I don't really care if it's more than -3 or less than -3. I only really care about more or less if it's 0. So in the bottom, 2 minus 2 is 0, but because of this plus, a little more than 2 minus 2, is that going to be a little more than 0 or a little less than 0? A little more than 0, right? I mean, if you have to, you like literally write down, okay, 2.1 minus 2. Okay, that's positive. So -3 divided by something close to 0, but a positive close to 0. So this is now what we looked at in warm-ups a few minutes ago. What's -3 divided by 0 but positive 0? What do you think, Tyler? It's negative infinity. Divide by a really small number, you get infinity, but then we got to worry about the signs. Negative divided by positive is negative. And then officially, any limit that's infinity is D and E. But I want to make sure we get the positive or negative part correct. Why don't you try number 8? So it's really similar. I mean, you can see right away you're going to get 0 in the bottom if you plug in -1. So you're going to need to plug in -1, but a little more than -1. So try number 8. So I plug in -1. I'm not worried about the plus or minus in the top because those aren't zeros. So I'm not worried about it. -1 plus 2 is 1. -1 minus 3 is -4. But the bottom one, -1 plus 1 is 0. But if I'm a little more than -1 and I add 1, is that 0 plus or 0 minus? Is it positive or negative? Good. I got 2 whispers of positive. But those are correct. And again, if you get stuck, especially with negative numbers, just think to yourself, okay, what's a little more than -1? That'd be like -0.999. And if I add 1 to that, then it's going to be positive. So what's my overall answer now? 1 times -4 divided by 0 positive. What's that turn out to be? Infinity, but negative infinity. Right? Because the -4 in the top. And then anything that's infinity is D and E. Okay? Good? Kind of weird. Like substituting 3 plus or 2 minus kind of stuff. Try number 7. So we substitute. I'm just going to substitute 5 to start with, and then I'll worry about if the minus sign matters or not. 0 over 3. Oh, it doesn't matter if it's positive or negative because it's headed to 0. So that's the okay part, right? Okay is good. That's just 0. It's 0 in the bottom that we have to worry about. All right, that's 1 through 9. 10, 11, 12. You tell me what's different about 10, 11, and 12. What do they have in common that is different from all the other limits we've done? Limits go into infinity, so something different is definitely going on here. X is getting really big for these. X is getting really big. Okay, so we kind of have to change our brain thinking a little bit here. Instead of dealing with X really small, or dividing by small numbers, now everything is getting really big. So in the top, if things are getting really, really big, which one of these terms matters the most if I'm going to plug in a million or a trillion or a quadrillion? Which one of those terms is the most important?
Negative 4x cubed.
Yeah, negative 4x cubed. Because if I plug in a million and I cube it and multiply by -4, then adding 2 is like inconsequential. Adding 9x even doesn't really matter. So So step one on these is grab the most important term from the top and from the bottom, and then we'll go from there. And we usually write these out of order to try to trick you, to force you to look, right? If we put them in order, the biggest term is first. That's the polite thing to do, but we don't always do that. Let's see, in the bottom, 7x to the fourth is the biggest term. So what matters in this, as x gets really big, is just the big terms. X goes to infinity, worry about the big terms. Okay, this is something I can work with. What can I do with negative 4x cubed over 7x to the fourth? Reduce the x's. So negative 4 over 7x. Okay, now I can just substitute. Substitute sounds a little weird if you're substituting in infinity. It still works though. Negative 4 over 7 times infinity. So if I take negative 4 and I divide it into 7 gabillion equal parts, what's that equal to? 0. Right? If I take the $4 that's in my pocket right now and I divide it among everyone in the world, everybody gets $0, basically. All right, let's try the same thing with number 11. Again, x goes to infinity. Infinity means you want the big terms. The big terms are what's important. So 4x cubed and 5x cubed. Oops, make sure you get the sign with it. Negative 4x cubed and 5x cubed. So what do you think that equals? I'd argue that's even easier than the last one.
Just
Negative 4/5, because the x cubes will cancel. And then lastly, let's see. We're doing all three of these because they're all the same type problem, but there's three different types of that problem. So we need to do all of them. Let's see. Again, grab the big terms. So 3x to the 5th from the top, 7x cubed from the bottom. The only terms that really matter. Again, we can reduce with the x's. But what happens here if I plug in infinity for x? 3 times infinity squared divided by 7. What's that going to be? 3 times really big number divided by 7. What's that? Infinity over 7. Yes. And what's infinity divided by 7? Say it. You're right. It's still infinity. Right? You take infinity and divide it by 7. It's still infinity. Which is D and E. All right, don't turn the page yet, because there is I hesitate to even show the shortcut, because people use the shortcut in the wrong place, when it would have just been easier to think through the process. So, like every calculus student knows this shortcut, so I'm going to show it, but I almost wish I hesitate because people use it in the wrong spot. So let me put the condition on it. If you have a limit as x goes to infinity. So you cannot use this shortcut if you have one of the other limits. But if x is going to infinity, then here's the shortcut saying, it's so fun, that's why we share it. Top no, bottom O, equal co. Top no, bottom O, equal co. Now, can you interpret what the heck that means? We're talking about which which is bigger? Which power is bigger? So if it's bigger on the top, like number 12, x to the 5th is bigger than x cubed, then no, there is no limit. It's infinity. Top, no. Number 12. Bottom, O. So if it's bigger on the bottom, that would be like number 10, then your limit is 0. Because eventually you're going to be dividing by a really big number. Equal co, so if the degree is equal, then, so what we're looking at is degree of top versus degree of the bottom. If degrees are equal, then you can divide their coefficients. Top no, bottom O, equal co. But only use it when x is going to infinity. It doesn't work for all limits. And that's the trick, is that somebody's going to look at, let's say, number 9, and they're going to be, oh, look, that's an equal co problem, so my answer is 1/2. Like, no, that doesn't even qualify. It has to be x going to infinity. So, great little rhyme to help with the infinite limits. Top no, bottom O, equal co. But please don't use it when you're not supposed to use it. And if it kind of doesn't make sense, then there's people who are like, I don't like that. I just want to think about which one's bigger and reason through it. And that way I can understand the problem rather than memorize the problem. And that's fine too. Top no, bottom O, equal co. All right, there's a couple more things that are sort of thrown into this lesson that we need to talk about. So we can do more notes at the top here. We kind of need to add another function to our parent function database. Like, I hope you know what y equals x looks like, and y equals x squared, and y equals square root of x. In fact, that's what we're doing in pre-cal today, is all the parent functions that you know. And you know a bunch of them. But we need to add one more, and it's this function that we use in calculus a lot. And you kind of just have to know what it looks like. I mean, I guess you could figure it out. If x is positive, so if x is 1 or 2 or 3 or 4 or 5, then x over x is just 1. If x is negative, so like negative 5 divided by positive 5, you get negative 1. And so it's a simple graph, but a graph you need to know, because they like to ask, AP likes to ask limit questions about this graph. Because if you come from the right, the answer is positive 1. If you come from the left, it's negative 1. Overall, it's non-existent. So, number 13. X minus 3, x minus 3. So what is that minus 3 in there with x? What does that do to the graph? Think back to your parent function transformation stuff. What does minus 3 in with x do to the graph? Do you remember? Which way does it go? Right 3. So this graph is going to look like this graph, except it's shifted to the right 3. 1, 2, 3. So it looks something like that. So the limit as x approaches 3. Well, it's definitely not negative 3 or 3. So looking at this picture, as x approaches 3, what's my y value doing? Is it approaching negative 1, approaching positive 1, or does it not exist? It doesn't exist, because they're coming from different sides, so it's non-existent. It would need to be a one-sided limit to exist. – 14 has things switched around a little bit, so you might just want to plug in. You could just use substitution for number 14. Plug in something a little more than 6 and see what happens. My guess is, since it's coming from the right, it's going to exist. and it's going to be either 1 or -1, but you'd have to plug it in to see which one would work. But I'll leave that for you. Fast forward to number 18. This will be the last one we do together. Piecewise function. So piecewise function, you can maybe see how piecewise sort of fits with one-sided limits, because if you're coming to 2 from the right, what does that mean? All of your values are a little more than 2. So if all of your values are a little more than 2, which branch, which piece will you be on, A, B, or C? If you want to approach 2 from the right, will that put you on branch A, branch B, or branch C? C. So I don't care about getting to 2, so I'm not going to use branch B at all. I definitely don't care about less than 2, so I'm not going to use branch A at all. All I care about is branch C, because I'm looking for x to be a little more than 2. So branch C is 4x plus 3. So it's still a substitution problem, but you have to know where to substitute. 4 times 2 plus 3, 8 plus 3 is 11. Number 19, pretty similar. You got 3 branches. You're at 2, but which 2 are you at? A, B, or C? Plug it in and find out. Okay, that's enough of me doing them. You get to do the rest of them. You still got 10 minutes left if you want to work on some of them. And maybe not have any homework for the weekend.